know when and how to apply linear motor technology. This requires that you know the components that comprise not only a linear stage, but the components that are used to make other linear actuators, such as ball screws, belts, and rack and pinion. I'll compare each technology using a few key metrics. The advantages and limitations of each mechanism are crucial when deciding how to apply the technology. By the end of this video, I expect you'll be able to more readily identify linear motor applications that may otherwise have been solved less effectively with a different the construction of the SigmaTrack 2 linear stage using this 3D model. In a linear motor, the motor coil propels itself along the magnet track. The motor coil is attached to the carriage, sometimes called a slide, and the load is bolted directly to the carriage. The carriage is held in place by linear bearings with rails secured to the base. The linear bearings are the only point of mechanical contact and frictional wear. This simple fact results in huge performance benefits for the SigmaTrack 2 linear stage, or any linear stage for that matter. There is a very small air gap between the motor coil and magnet track, and the position of the carriage is reported to the control system through a linear encoder. The encoder has two parts: the scale mounted to the base and the moving reed head. Other parts of a typical linear motor stage are the cable management system and end stops. Now let's consider a few competing mechanical technologies, starting with a typical ball screw. These also have a carriage that moves on linear bearings and rails, but the force to move it is transmitted through a nut from a rotating screw. This nut is typically comprised of a system of enclosed recirculating ball bearings which minimize friction. The screw is, of course, driven by a rotary motor, and the encoder in the motor provides position feedback to the control system. The screw is held in place with bearings at each end and connects to the motor through a flexible coupling. The ball screw is the standard go-to actuator for a wide variety of applications. Similarly, a belt actuator also has a carriage with linear bearings moving on rails. This carriage is driven by direct connection to a timing belt riding on two pulleys. The pulleys are held in place with bearings and connect to the motor with a flexible coupling. The encoder on the motor provides position feedback to the control system. A rack and pinion system is typically comprised of a motor that drives a pinion, moving itself along a fixed rack like a train on a track. The motor is mounted to the carriage, driving the pinion through a gear reduction to move the entire assembly. Now let's look at how each of these technologies compare in metrics such as initial cost, speed and acceleration, and other factors listed in this table. I'll define each of these metrics and then discuss the strengths and weaknesses of each technology. Please bear in mind that this is not a strict and absolute evaluation, but represents general industry trends. Let's start with the bottom line, initial cost. As we'll see, the linear motor generally has the highest overall performance. It goes to reason, therefore, that the initial cost is also generally higher than other technologies. Ball screws are significantly less expensive than linear motors, but they are more expensive than belt actuators, which tend toward the low end of the cost spectrum. Rack and pinion is a little tough to compare. These tend to be used in physically large systems with much larger and heavier payloads. The cost of a rack and pinion is far lower at that scale than linear motors, ball screws, and belts. But at a smaller scale, that advantage is often less distinguishable. How about speed and acceleration capability? Motion control systems have the need for speed. Faster, better, and more means a quick return on your investment. The linear motor can accelerate quickly to reach high speeds, typically around 5 meters per second. It is the performance champion for the mechanism with both high speed and acceleration. Screw-driven actuators can have strong acceleration, but above the critical speed, a screw will oscillate. This critical RPM design limitation is dependent on the diameter and length of the screw. The screw lead can be designed to move further for every turn. This increases the linear speed for the same motor RPM, but it also means more motor torque is required to move the same load. The result is that a larger and more expensive motor may be required to move at fast speeds. And occasionally these constraints have a snowball effect, resulting in a very oversized or even impossible solution. Belts can also be fast, about the same as linear motors, but as we'll see later, they have nowhere near the same precision. Rack and pinion systems can reach very high speeds, higher even than linear motors, but they typically don't accelerate quickly since they are designed to move large and heavy loads for longer distances. That brings us to length. The large systems driven by rack and pinion can be quite long, and it is cost-effective to increase the length with additional rack segments with little impact on performance. Linear motors can also be used in applications with long stroke, but the cost of magnet track and absolute encoder tape is significant. Performance, however, is unaffected by overall length. Ball screw length is limited once again by the critical speed of the screw. Longer screws begin to oscillate at a lower RPM and negatively impact tuning by lowering resonant frequencies. We'll discuss this more later. A larger screw diameter helps achieve usable speeds, but this means large motors are required to drive the longer screws, even with a small load, unless the speed is very slow. Belt drive designs are easily lengthened with minimal increase in cost. However, the effective belt stretch becomes proportionally worse, resulting in reduced accuracy and repeatability. And like the ball screw, with increased length comes decreased stiffness and the problem of lower resonant frequencies. Horizontally oriented motion is the most common, but vertical or inclined axes are required in many applications. This means the force of gravity is constantly pushing the load down. This force must be overcome by the motor while the axis moves or holds position. When the machine powers off, a braking system can prevent the vertical axis from falling. Rotary brakes are commonly found in servo motor designs to lock the motor shaft when powered down. This makes the ball screw or belt an excellent choice for vertical loads. A vertical rack and pinion also works well for the same reasons. Linear motors are a bit more complex with vertical loads. A counterbalance or linear holding brake should always be used. A linear holding brake may be mounted externally to brake against the rail. Machine rigidity or stiffness and its inverse, compliance, is important to understand. Every mechanically connected element has a level of rigidity, a spring constant. This rigidity, along with the mass of each element, defines the natural frequencies of oscillation for the system. If these frequencies are too low, the release of energy can cause a significant disturbance to the motor. This interferes with the control system algorithms that position the load. Belt drive systems generally have the lowest rigidity and therefore the lowest natural frequencies. The belt is like a spring, and there are natural frequencies between the carriage and the pulleys. Another loss of rigidity occurs between the drive pulley and the motor coupling. As the motor begins to turn, first the coupling deflects according to the spring constant. Then the belt deflects before the load finally moves. The rigidity is further complicated since it depends on the position of the carriage and resulting length of belt in direction of the force exerted through the pulley. Ball screws have a much higher rigidity, but the same principles apply. The motor turns the coupling, which deflects, which turns the screw, which also deflects to some extent. Long, thin screws will have lower rigidity than short, wide ones. Rack and pinion is a little different. These maintain a constant and relatively high rigidity at the point of mechanical connection, regardless of the load position. But oscillations are likely to originate within the load itself if it is large and complex. But the most rigid of all these actuator technologies is the linear motor. There is no coupling or mechanical linkage to deflect. The load is connected directly to the motor through the carriage. If there are any frequencies of oscillation, they will come from the load itself and not from the mechanical system. So you see how rigidity and resonant frequency are related to load mass. This is summarized in a key performance metric called the load-to-motor inertia ratio. Servo systems are commonly sized for a load-to-motor inertia ratio less than 10:1 for acceptable control of the load by the motor through the flexible coupling. However, this ratio is of no importance in a linear stage because the motor is directly coupled to the load. Think of the load on the linear motor as nothing more than an extension of the motor itself. A linear motor has no coupling to reduce the rigidity of the system. Load mass, nevertheless, is important for linear motors as it limits the acceleration and deceleration rate according to Newton's law. It also affects bearing life. Low friction also means that nearly all the power to stop a moving load must be supplied by the electronic drive system, which can also limit the maximum load. The clear winner on moving heavy loads is the rack and pinion. These are often used on large gantry systems. Ball screws can also be sized to move very heavy loads, commonly applied in applications with moderate length and speed requirements. However, the inertia ratio and low resonant frequencies associated with heavy loads tend to limit the application. Belt mechanisms tend to have lower practical weight limits, as do linear motors. Acceleration and therefore top speed can be limited with heavy loads. Performance criteria and load mass are among the most important elements in mechanical system selection, so it is fundamental to understand these well. The performance of linear actuators can suffer from an effect called backlash. This is lost motion when the mechanism reverses. The ball screw has a level of backlash between the nut and screw. This can be reduced with preload, but preload causes the nut to wear out faster. For the belt system, backlash occurs between the teeth of the belt and pulley. The same can occur between the teeth of the rack and pinion. Manufacturers have developed ways to reduce the backlash in actuator technologies and electronically compensate for it in the control system. But there is always some level of backlash, and it tends to get worse as the mechanism wears. It means that the position of the load once again cannot be exactly determined by the position of the motor encoder, and it can also lead to tuning instability and noisy operation as the load effectively disconnects from the motor for a short time upon reversal. The linear motor is the only mechanism that can truly claim zero backlash. Position feedback is measured with a linear scale, with the reed head, carriage, and load bolted together as one piece. Rigidity, load mass, inertia ratio, and backlash are all interrelated factors that worsen the position settling time of a mechanism. Position settling time is the time delay between the end of the commanded move and when the mechanism actually stops. Reducing this delay is especially important for applications with many short moves. Waiting for the machine to stop can represent a significant fraction of the cycle time. The settling time in a linear motor can often be reduced to zero with good tuning due to its high rigidity and zero backlash. although it may be necessary to mitigate vibrations originating in the load itself. Achievable settling times for the ball screw and belt generally follow the level of mechanical rigidity and backlash, with screws generally outperforming belts. The same goes for rack and pinion, although fast moves and low settling time are typically not the focus with these larger machines. Remember that the position of these mechanisms is measured through the encoder of the rotary servo motor. The encoder may indicate that the load has settled with a low settling time, but what that really means is that the encoder has stopped moving. The load may still be in motion and not yet settled or experiencing vibration and oscillation. Rigidity and backlash interferes with the measurement of settling time through the encoder of a rotary servo motor. However, in the linear motor, the encoder is fixed to the load itself, reporting the true settling time of the load. Backlash and rigidity also contribute to a mechanism's positioning accuracy and repeatability. Accuracy is a measure of the deviation from the ideal, in this case position. If the machine is commanded to move 4 millimeters, does it move exactly 4.00000 millimeters? Or if you were to measure it externally, did it only move 3.999? What's often more important is repeatability, also called precision. Because if the machine can move to 3.999 repeatedly when you command 4.0, then simply adjust the command until it does repeatably move to the required position. The control system measures position at the encoder. Rigidity and backlash add an element of uncertainty to those measurements. Additionally, the manufacturing process of a belt, ball screw, or rack and pinion will affect the accuracy and repeatability. Only the linear motor, by natural design, measures the load directly and moves it without the backlash and compliance problems that can plague mechanical actuators. You may have been thinking, why not compensate for the shortcomings of ball screws, belts, and rack and pinion mechanisms by adding a linear encoder? Yes, this is possible, and at Yaskawa we call it full closed loop. This allows the position loop of the rotary motor to be closed by linear encoder feedback. However, adding a linear encoder adds significant cost and complexity. The linear scale must be accurately placed. The reed head clearance to the linear scale must be accurately aligned. And now you'll have a cable track for cable management of this encoder on the carriage. Most servo amplifiers don't support a second encoder input without additional hardware cost. Servo tuning will also be affected and must be completed again. In short, if the performance of an existing system must be improved, then full closed loop is a viable option. But it is generally not a significant cost savings compared to using a linear motor in the first place. Adding full closed loop will improve repeatability and accuracy, but it does not do much to improve rigidity, settling time, and wear. So ask yourself the question, will a linear encoder on a belt, ball screw, or rack and pinion really save money in the long run? There's no avoiding it. All mechanisms wear. Let's take some time to understand what part of the mechanism wears and what happens to the system performance as a result. In the linear stage, only the linear bearings wear out, but until they utterly fail, that stage will position accurately, at least in the linear direction, while pitch and yaw and roll of the carriage may deteriorate over time. Some linear bearings require lubrication, but self-lubricating linear bearings are commonly available, such as those used by SigmaTrack 2. The same applies to linear bearings on a ball screw, belt, or rack and pinion. But these mechanisms have other moving parts that wear out. The screw itself, the nut, the bearings on the screw, motor bearings, belts, rack and pinion, and gearboxes all wear out even with regular lubrication. From day one, the performance of these mechanical systems begins to decline. The backlash and stiffness get a little worse every day. Therefore, expect positioning time, accuracy, repeatability to continually degrade as time goes on. The linear motor bearings do eventually wear out, but quite gracefully by comparison. Different mechanisms are best suited for different industrial environments. Consider the magnetic field of the magnet track of a linear motor, which may attract particles. A bellows protection system will help keep particles out of the magnet track. While linear encoders don't require a clean room, they do their best in a reasonably clean environment free of excessive dust and oil. The linear scale can still work with some interference, but for very dirty environments, consider a custom linear motor with an inductive or magnetic linear encoder. The ball screw is used commonly in machine tool and other dirty environments, although the screw must be protected. Belts and rack and pinion also work well in many environments. Clean rooms are on the other side of the spectrum, where it is critical to reduce the number of microscopic particles emitted by the actuator. Linear motors can be easier to make clean room compatible. The many wear points of ball screws, belts, rack and pinion, or other mechanisms with mechanical power transmission are generally less desirable for clean room operation due to the number of particles ejected during operation. When selecting the right actuator for an application, consider the long-term cost and performance. There are applications with specific constraints which logically eliminate linear motors from consideration. Other applications have long been the strength of linear motors: long stroke or high speed, fast acceleration, precision and accuracy. But there's a middle ground where linear motors are often overlooked in favor of the traditional solutions like ball screws, belts, or rack and pinion. Solving these applications with linear motors can save money in the long run while providing exceptional and stable performance over the life of the machine.